The answer is both exciting and alarming. In the vast areas of the universe, scientists have discovered vast cosmic voids, where instead of the light of millions of galaxies and countless stars, there is only darkness and emptiness. Not only do these strange space-time anomalies stand out from the rest of the cosmos, they also seem to defy the known laws of physics, possibly representing an entirely new phenomenon. With no detectable matter, these vast voids challenge the standard expectations of Einstein's equations of relativity and raise questions about the unified structure of the universe. The great size of these regions, which seem to contain nothing, defy the normal rules of cosmology. Their scale not only defies our physical laws, but also pushes the limits of imagination. These potential gaps in the fabric of space-time are enormous, spanning millions of light-years and comparable in size to the largest known galaxy clusters. By comparison, a light beam traveling at nearly 300,000 kilometers per second would take thousands of years to travel through one of those vast empty fields. These regions are so large that they can dwarf some of the largest known structures in the universe, such as the Virgo cluster or the Laniakea supercluster. They represent a mysterious absence, with very few galaxies and almost nothing in their haunting voids. The confusing thing is that these areas are not completely empty. Scientists have discovered isolated galaxies that are like lost beacons in an otherwise barren space. The presence of these galaxies makes the voids even more terrifying. We are facing a cosmological discovery that could radically change our understanding of the universe. What causes these huge empty areas in tissue space? Are they the result of natural cosmological processes, or do they indicate phenomena we do not yet understand? These voids that confound scientists are vast cosmic voids, empty spaces of such epic proportions that they cannot exist by chance. They must serve a unique purpose or result from incredibly violent cosmic processes. The giant voids between galaxies and galactic areas are the most enigmatic phenomena in the universe today. Even black holes are better understood than these voids. A notable example of these structures is the Boötes void, which NASA describes as a vast void spanning millions of light-years with no detectable matter. This void was first discovered in 1981 by the astronomer Robert Kirshner and is one of the largest known voids, with a diameter of about 330 million light-years. Kirshner and his team called their discovery the Big Nothing. At the time, astronomers believed they had discovered a unique anomaly. Little did they know that this void was not the only one. Many such voids are known today, some even larger than the Boötes void, such as the Eridanus void, which stretches over 500 million light-years, and the North Local void, which also reaches considerable dimensions. There are thousands of these voids, and together they make up a significant part of the universe. When talking about void, darkness, and emptiness in the universe, terms like dark matter or dark energy naturally come to mind. Whether and to what extent these phenomena are related is an interesting question. Some hypotheses suggest that the size and distribution of vacancies may provide deep insights into the nature of dark energy. Dark energy is thought to be responsible for the accelerated expansion of the universe, but it may also play a mysterious role in the formation of these voids. From particle physics, we know that where there is no visible matter, there are probably invisible forms of matter that we cannot see simply because they do not emit light. In void-like places, obscure forms of dark matter may be more common than elsewhere in the universe. Therefore, these structures are highly sought-after research targets. To make the dimensions of the gaps more meaningful, we can imagine the known universe as a football field. Galaxies and galaxy clusters would represent small patches and clusters in that field, while voids occupied most of the region. Galaxy clusters and superclusters make up perhaps only about 10 to 20% of the mass of the universe, while empty space and the interstices make up the rest. It reminds us that, according to scientists, the universe is about 85% dark matter. So, are these cleared spaces and their distribution like mirrors that show the distribution of matter in the universe on a large scale? Do voids help us understand effects like gravity and dark energy? Voids allow cosmologists to study the effects of gravity in environments where large amounts of visible matter are not directly present. Gravitational effects in and around the vacuum, however, only manifest themselves to us through the motion of visible matter. For example, the few galaxies within these voids and their gravitational effects become apparent when we study the light from objects behind the voids. As great as the void is, it reaches a spatial conclusion at some point. If there are galaxies beyond the void, their light travels through the void to us. Some observations can provide information about how gravitational forces act at great distances and with little visible matter, which in turn can lead to conclusions about the distribution and properties of dark matter in the vacuum. The voids are also perfect for studying their shape and thus the growth rate of these colossal cleared spaces, which in turn allows conclusions about dark energy. To do this, the researchers studied the geometry and dynamics of the cavities in great detail. Imagine that our galaxy is in one of these voids. Let's go back to when astronomers first realized that our Earth is a planet in a galaxy. Astronomer Edwin Hubble first realized in the 1920s that there are more galaxies in the universe. Hubble first saw the Andromeda Cloud and other similar objects in 1923. Soon after, Hubble succeeded in proving that these nebulae are independent galaxies outside our Milky Way. This discovery was of course amazing, and you can imagine how it changed the cosmological understanding of people at the time. Since then, the universe has grown and grown.
Today we know about 2 trillion galaxies and can see more than 45 billion light-years in both directions with powerful telescopes. If Hubble had lived in a galactic vacuum, he would not have been able to discover another galaxy in his lifetime. He would have seen nothing but a blur and may have thought that the universe beyond his cluster of stars was a vast void. It was only in the 1960s that our technology was so advanced that we could see as far as a scientist in a vacuum would have to see to spot his first galaxy outside his OWN. An anecdotal explorer in the void may find the universe very sparsely populated from his perspective. In the 1980s, we may have encountered the first cluster of galaxies, and we would be surprised to find in a scientific journal that there are mysterious clusters of galaxies in the universe for which the science of this fictional world has no explanation. In our case, the picture is completely opposite. We humans began to explore our galaxy, which for a long time was the center of the cosmos for us. Then we looked at the sun and other planets and finally realized that all the stars are other suns and that there might be planets. Our science has grown linearly from our perspective, and discoveries that were initially inexplicable have provided new clues about what the world and the universe really are like. The voids show us that our view of the universe is still very one-sided, and that what we consider normal may be the exception elsewhere. Further probing these gaps, scientists began to uncover subtle but fascinating clues about the evolution and structure of the universe. For example, the arrangement and distribution of galaxies in these voids can provide valuable information about the large-scale structure of the cosmos. In this context, the study of the cosmic web, the vast network of interconnected filaments and knots of galaxies and dark matter, becomes particularly interesting. In the cosmic web, voids act as huge voids that separate these filaments. By analyzing the shapes and sizes of these voids, scientists can gain insight into the underlying physics that governs the formation and evolution of the universe. One of the most exciting aspects of studying the vacuum is its potential to illuminate dark energy, a mysterious force that is believed to be driving the accelerated expansion of the universe. Voids are a fundamentally unique environment to study this phenomenon. Because they contain significantly less matter compared to denser regions of the universe, cavities provide a relatively clean laboratory for studying the effects of dark energy on a cosmic scale. By accurately measuring the expansion rate of these voids over time, scientists hope to gain important information that will help refine our understanding of dark energy and its role in the cosmos. Furthermore, the presence of isolated galaxies in these voids raises interesting questions about galaxy formation and survival. How can these lonely galaxies exist in such seemingly inhospitable environments? The study of these isolated cosmic islands can reveal important information about the conditions for the formation of galaxies and the factors that influence their evolution. These galaxies act as natural laboratories, allowing astronomers to observe how galaxies behave and interact with their environment without significant external gravitational fluxes. These observations allow us to reveal new insights into the processes that form galaxies and their potential to adapt and evolve in the most unexpected cosmic landscapes.